Here are a few topics we can expect to cover during this lecture. This includes learning about stereochemistry, why molecules shape matters, exploring chirality and mirror image molecules, understanding molecules in 3D, and most importantly, our virtual simulation. Please don't be afraid to ask any questions throughout this session, as a few concepts can be confusing for beginners. Now, I'll pass it back to Azzy.
Yeah, that's exactly right. So now that you have the context for what this meeting is for and what you can do with this knowledge of stereochemistry right after, let's move to our main topic of today. So most of you guys might not know what stereochemistry actually is unless if you've been in a more advanced bio or chemistry class. Essentially, it's the study of three-dimensional spatial arrangement of atoms. So what that essentially means is how these different molecules are connected in three-dimensional space, how the elements are arranged, because the way you do that directly affects chemical properties and interactions. So molecules might have the same exact parts, but behave differently because of their shape, and this affects a lot of different things from smell to drug effectiveness. So for example, there might be two cakes with the same exact ingredients, but one of them has sprinkles on top and the other one has sprinkles mixed in. I mean, clearly these use the same exact recipe, but they taste and have a different texture, and some people might not actually like the cake with sprinkles mixed in, so it is very important to pay attention to molecular shape and structure today. So with that essential concept in mind, let's talk about chirality, which is the main concept of stereochemistry. So essentially what chirality is the property of an object or a molecule to have a non-superimposable mirror image. So that was just a lot. So if you guys don't know what non-superimposable means, let's first look at what superimposable means. Superimposable means that two objects can be placed on top of each other and align perfectly. So if you have a water bottle and you have another identical water bottle and you line them up and you take a photo, it literally looks like there's just one water bottle. But if you put one of your hands on top of another one of your hands, that might not necessarily be true. So a molecule is chiral if it cannot superimpose on its mirror image, like the water bottle I just explained to you. On the other hand, a molecule is achiral if it can be superimposed. So it is very important to remember that chiral means it's non-superimposable and achiral means it is superimposable. So a very key feature of these chiral molecules that are not superimposable on the mirror images are having chiral centers. So essentially, it's like an atom in a molecule that is bonded to four different substituents, or essentially it has four different connections. And the way that it has these connections make it impossible to be directly laid onto another one that is connected differently. That was very confusing, so I'll give you some time for that to sink in. But if you're confused about chirality and superposition, feel free to ask in the chat and I can clarify before we move on to a first problem.
Maybe something to clarify, as this may not be clear to everyone. Substituents aren't just the adjacent atoms, but the whole chain that follows. For example, if both neighboring atoms of a carbon are, for example, another carbon atom, it is different. The substituent is different if there are, let's say, 11 carbon atoms, and on the other side only 2. So you have to look at the whole molecule based off the chiral center.
Yeah, that is exactly correct. So now that you guys know what chiral and achiral and superimposable and non-superimposable mean, and also how like a chiral center just means you're connected to four different parts, let's test our understanding with a very basic question, and I may or may not have given this away on the previous slide. But please answer A or B in the chat. Are our hands chiral or achiral? Okay, I see an overwhelming amount of A's and essentially no B's. And you guys are exactly correct. Our hands are chiral, and not just because I gave it away in the previous slide, but also because of the fact that if you look at your hands side by side, your left and right hands are mirror images of each other, but they're not identical. So if you stack one of your hands on top of the other one, they don't look exactly the same. You don't just see one hand there, you can see the thumb sticking out on both sides. So clearly, those are not the same, even if they're mirror images. So that means our hands are chiral. So now that you have this down with some basic objects like a water bottle, like your hands, let's move on to the next question and with some actual molecules here. So which molecules do you guys think are chiral based on what we said in the previous slides? And you can just put the numbers in the chat. And you can use the same exact concept that we just did with the hands and the water bottles. If you flip its mirror image and put it on top of it, is it going to look like they're exactly the same, or do they stick out differently? And I'll give you guys some more time to answer this one. You also don't need to know what these molecules actually are as long as you're able to imagine the mirror image and see if it does the same exact thing. I'm going to give you guys a hint and 1 or 2 more minutes to answer. Because I understand it is very easy to mix up chiral and achiral. But remember that your hands are chiral, a water bottle is not. And if you keep that example in mind, you can probably sort out the rest. Okay, I saw at the beginning everyone was saying 2, 3, and 7, and then everyone switched to 1, 4, 5, and 6. So good job. After that hint, the answers to this one are indeed 1, 4, 5, and 6. And if you guys were initially confused, this is because not only do they have these chiral centers and these connections, but also they lack a center of inversion that would make the overall molecule symmetric and chiral. So essentially, if you look at example number 1, and you just flip it over and lay it on itself, the OHs don't exactly line up. And you can also see this with example number 4, 5, and 6. When you flip these over, they don't look exactly the same, either because they are connected to different atoms or because they're sticking out in different ways. So for example, for number 5, there's a connection to a Br on the left and to Cl on the right. If you flip it over, it would be connected to Cl on the left and Br on the right. So when you place it on top of itself, those are clearly not the same atoms. For number 6, you can see that Cl on the left has a dash, which essentially means that it's sticking behind, and that Cl in the right has a wedge, which means it's sticking out in front. And you don't need to know that when you flip these over and lay them on themselves, those are clearly not the same exact orientations, and they're not stuck in the same exact way. So that is also known as a meso compound. A meso compound is a compound that doesn't have asymmetry like these molecules, and they would have a center. So for example, you guys said 2, 4, and 7 at the beginning. Those are not chiral, but those are meso compounds because they have a stereocenter and a plane of symmetry. So as you can see with the dashed line, no matter how you rotate this molecule onto itself, it's going to be identical and has a plane of symmetry. So I think the main concept here is that you guys are mixing up chiral and achiral. So just remember that chiral is like your hands. When you reverse them, they have to look not exactly the same. And for an achiral molecule, when you reverse it, it should look nearly identical. You'll also see that on 2, 3, and 7, they have lines of symmetry. And some of you guys might be confused by number 3, because if you flip it over, doesn't that mean the H is going to be sticking out in a different direction? Well, you might have to look intrinsically at how the bonds are arranged. The O is still connected to the H when it is reversed, and it's just drawn like that. But in reality, it's going to be stuck out, and when you reverse it, it's still going to be laid on itself. That might be a little confusing, but you guys all worked it out in the end. So let's cover a new concept building on top of this. So we're going to talk about stereoisomers. And has anyone ever heard of isomers or learned about them before in a biology or chemistry course? You guys can type yes or no in the chat real quick, or give me a thumbs up. That's great to have some background knowledge, but essentially, for those people who haven't heard of isomers, they're molecules with the same formula, but the atoms are connected differently in different three-dimensional arrangements. So for example, you'll see cis and trans butene. These two things have the same exact atoms in them, but they're just connected in different ways. You can also see that these are chiral and non-superimposable. When you reverse trans butene and put it on top of cis butene, it does not look the same, because where there's a CH3 group, you see that there is an H on the trans when it's reversed. So they behave very differently. So since you guys know what isomers are, let's look and take a look at 2 types of these stereoisomers. So first, let's talk about enantiomers. These are chiral molecules that are mirror images of each other, just like our left and right hands. So just think of these as chiral. They have the same atoms connected in the same order, but their 3D arrangement is opposite. And this different arrangement can lead to one enantiomer being very effective in treatment, for example, while the other one may be inactive or very. So you might ask, literally, what is the difference between enantiomers and chiral molecules? Like, aren't they the same? Well, the difference is that chiral molecules don't have to necessarily be mirror images, as long as something's opposite imposed onto itself is not lining up, then it is chiral. But if something is itself reflected and put on itself and it still does not look the same, then it's an enantiomer, because it's both a mirror image and also chiral. Does that make sense to everybody? Okay, I'm assuming that makes a lot of sense. So just keep in mind that enantiomers are mirror images and chiral. So the second stereoisomer is the diastereomer. So very similar to the enantiomers. They have the same atoms connected in the same order. However, their spatial arrangement is different, so it doesn't produce a mirror image. So they are not mirror images of each other, but they are still chiral. So they often have very different physical and chemical properties, not similar ones. So that might be very confusing. They're different configurations at the same chiral center. So for example, you can see in the first diastereomer on this slide that the pH and H are connected differently in the trans and cis versions. So when you reflect these are clearly not reflections of each other, but when you overlay the reflections, they also don't line up. So not only are they like connected differently and not reflections, but they also don't line up when the reflections are reflected. That is a little bit confusing, but if you look at the second example, that might make a little more sense. If you see that this Cl has a solid line, so that means it's sticking out front, and this second Cl is sticking out behind. And when you reflect these, you can see that they are not mirror reflections because the atoms themselves are connected differently. And when you lay them on each other, they also don't line up to be the same molecule. So you see that not only are they not reflections, but they are also chiral because they are non-superimposable. That might be a little harder to understand than the enantiomers, but does that make sense, and can you tell the difference? All right, for the people who don't think it makes sense, hopefully the next diagram should explain this well. Here is a diagram on the relationship between enantiomers and diastereomers. you can see that the ones that are literally reflections of themselves are enantiomers. But for example, if you move this second group onto the first one, they are not going to look the same because they're stuck out in different directions. But if you can see here for the enantiomer in the top right corner and the diastereomer in the bottom right corner, you can see that these two are like connected entirely differently. So if I reversed one of them, they don't look exactly the same as like a mirror image of the other one. And when you overlay them on top, they are still not going to look the same. So that is the intrinsic difference. So for a good way to remember this is for the enantiomers, they're reflections and they're chiral. And for the diastereomers, they're not reflections and they're not chiral. So if you think of diastereomers, it starts with di, kind of like disagree. So the molecules are disagreeing with each other. They're not reflections of themselves. They're intrinsically different, but have the same atoms. They're just connected completely differently and are just reflections. Does that make a little more sense? And if you have a question, feel free to drop it in the chat so I can clarify before we move on to problems involving these. Okay, that makes a lot more sense. That's good. So now that we learned about the two types of stereoisomers, I'm going to ask now, what is the relationship between the molecules in this picture, enantiomer or diastereomer? And you can put A or B in the chat. If you guys don't know what the solid or the dashed lines mean, just assume that they're a different type of bonding. So when you reflect one of these, are they the same? Also, a hint that I'm going to give before you guys put anything in the chat is that something doesn't just have to be directly reflected. You can also rotate it around to lay on top of another one to see if they're identical. Okay, I'm going to give a hint. When you rotate these or reflect them, do they look like mirror images? I'm going to give you guys a reminder that enantiomers are the ones that are mirror images, and diastereomers are the ones that are connected like totally differently. And remember that these solid and dashed lines mean completely different ways of connecting molecules. So don't assume those two are the same. Okay, I see that a lot of you guys changed your mind. These are diastereomers, so the answer is, yes, the answer is A, because they are not mirror images, but they have the same molecules with different configurations. So if you see all of these little triangle-looking wedges and dashes, they all look the same. It's not like one of them has like a Cl or something, so they're all connected to the same, and there's 5 of them on each one. So clearly, these are the same molecules with different configurations. But if you rotate them or reflect them onto each other, they don't look like mirror images or reflections, because as you can see here, for example, there is a solid bond here and there's a dashed bond there when it's reflected. And even if you rotate them, you can see that the solid and dashed orientations are totally different. So both of them have 5 bonds, but completely different positions. You can also see this image where I reflected and rotated one of them and put them on top of the other one. You can see that here some of them are solid and some of them are dashed on the different molecules. So they're not mirror images, and they're also chiral because when you reflect them and superimpose them, they are different. So you guys saw a lot of these wedges and dashes and things in the previous questions. So kudos to you guys for identifying those, even if you don't necessarily know what a wedge or dash is. So I'm going to give you a tip to identify those now for future problems. For a dark or shaded triangle, it's called a wedge, and it basically means that the bond points towards you out of the page. For the dashed lines in the dashed triangle, it's called a dash, and that means the bond points away from the viewer behind the page. So if you see these 2 3D images where there is a dark triangle wedge, it means that the atom is pointing towards you on a sheet of paper, if you see this wedge that is like dashed and it's going behind, it's a dash and it basically means that it's like hiding behind. So if you look at this flat image on a piece of paper, you can imagine certain parts are sticking towards you, certain ones are sticking away, and certain are just straight and on the same plane of the paper. You can also see this with the other example, the dash away and the wedge towards. You can see that some of these in red are pointing towards you, and some of these in green are pointing away. So does that make sense to everyone? Okay, that's awesome. So now for the people who have paper or have access to a computer or tablet, let's take a brief second to practice drawing with wedge or dash notation. So gray molecules are carbon, and you just draw them as connected lines. That's known as a bond line formula. So for example, if you see these 4 C's connected, it's just this line, and you can see that each endpoint of the line is just a carbon. Green, white, and red molecules are hydrogens, and you can either draw a solid triangle or a dashed triangle to represent if it's sticking out in front of you or behind you. So I'll give you guys a second to either get out a sheet of paper or use this free drawing tool. It's called Clucky.com to either use your mouse or like a stylus or something to draw this one out. And if you don't have a piece of paper and you also don't have a tablet and you also don't have a computer, feel free to let me know and we can also look at other people's answers after this one. As a reminder, the carbons are just connected by straight lines, and where the lines turn and the endpoints each represent one carbon. And in addition, you can use the wedges and the dashes to represent the hydrogens. You also don't need to color code this one if you don't want to, but the different colors help you understand which part is sticking out in front and which one's sticking behind. For the hydrogens that are in the same plane as you can just straight up use a line for that.
I have a
So just,
question.
yes, go ahead.
Could you repeat what we need to do is because I missed that part.
Yeah, no problem. So what we're doing is you either get out a sheet of paper or you go to Clucky.com, which is a free drawing tool, either on your computer or on like a phone or tablet. And you can draw this molecule on the picture using wedge dash notation. So if you recall in the previous slide, wedges mean that something is sticking out towards you, dashes mean they're sticking away, and a line just means it's in the same plane of a piece of paper or is flat. So if you see this molecule, there's red molecules that are sticking towards you, there's green ones that are sticking away, and these white hydrogens are just in the same plane of paper, so you can just use a line. For the carbons that are connected, those are gray, and each endpoint or intersection of different lines represent a carbon. So you can include both a carbon skeleton and these connected hydrogens using wedge dash notation to draw this molecule.
Oh, okay, thanks.
Yes, no problem. And just indicate in the chat when you're finished with your drawing. I'll provide like 3 to 5 minutes to do this one, since you guys need some time to get paper and to also open things up. When you guys are done, for the ones who did it digitally, if you could take a screenshot and put it in the chat. For the people who did it on paper, I'll have you guys show it to the camera in a second. Okay, awesome. Now that it is 3:40, if the people who did it digitally send a screenshot in the chat, and those of you who did it on paper, if you can turn on your camera and show it to us, or send a photo of it in the chat, that would be awesome. Okay, I do not see anyone with their cameras on, so if you want to show your paper drawing, feel free to just take a photo and put it in the chat. Okay, I got a pretty good structure, and I got a pretty good impression here as well. So here's a good example of how the molecule would be looking like. As you can see, with each endpoint, excluding the ones that are connected to like the hydrogens, obviously, there is a carbon. And also for the solid triangles pointing towards you, those are the hydrogens at you, and for the dashes, they are going behind. Okay, that's awesome. If the structure drawing confused you, we will be emailing out these slides after the event so you can look over them again if you want to practice. So now that you guys practiced with wedge and dash notation, I'll give you guys one more question about diastereomers or enantiomers. So this is a little more difficult one, but now you guys understand what wedges and dashes mean as part of the structure. Put A if it's diastereomers and B if it's enantiomers. And what is the relationship between the molecules in these pictures? This is a little bit of a trick question. Remember that I told you that wedges and dashes are connected totally differently? But now you know that a wedge is something pointed at you and a dash is behind. So think about what will happen if you rotate the second molecule. Will that wedge still be pointed away, or will it be pointed towards you? I see some division in the chat. I would say as a tip, imagine the molecule that is pointing towards you and the one that is pointing away. Okay, I see an overwhelming amount of B's, and that is correct. These are enantiomers, and if that confuses you, that's because when you reverse this one, the part that is sticking behind ends up sticking in front. So it actually looks like the mirror image of the first one. But when you move it on top, it's still non-superimposable. Does that make sense to everybody? So eventually, in more advanced stereochemistry problems, and also in an organic chemistry class, they'll give you a lot of these, and you'll have to imagine how the molecules rotate when you reverse them on top of itself. So the question that you just answered was about ibuprofen. So this was R and S ibuprofen, which just indicate the two forms. Racemic ibuprofen has equal quantities of R and S ibuprofen and is commonly found in the pain relief medicine you might have taken before. So S ibuprofen, the one with the dash, is the active form that stops enzymes that cause pain. But the R ibuprofen, which has the wedge that's pointing towards you, is basically useless. So 50 to 60% of the inactive R ibuprofen actually slowly turns into S ibuprofen after you swallowed the medicine in your body. This is called chiral inversion, and it's basically as it's rotating and going onto itself, it's literally changing into the other type and getting more useful as time progresses. This is why when you swallow ibuprofen, it doesn't suddenly make all your pain go away. Only after 15 to 30 minutes maybe, you start to see your aches and pains go away, and this is because chiral inversion happens, because enzymes and gut bacteria might bump into or interact with this molecule and change its handedness, essentially, so that it turns into the one that is actually helpful to you. Does that make sense to everyone? Did anyone know that ibuprofen used to be an isomer? Yeah, unfortunately, we can't make all of it suddenly turn into the useful version of it or separate them effectively and cheaply. So that's what happens, and that's why you wait. Oh, that's good. You learned it recently in AP Chem. All right, so we were going to run through a short meter rotation activity, but we're running a little short on time, so I'll give you a quick intro on what this is, and you can always review it in the slides after. So essentially, mutarotation is how molecules rotate light. And for example, glucose is a sugar that exists in two slightly different ring forms that are called the alpha form and beta form. When glucose is dissolved in water, these two forms slowly convert into each other, just like how ibuprofen does that. This ongoing interconversion is called mutarotation, and it changes how light is being rotated through the glucose molecule. A device called a polarimeter is used to measure this change and observe the mutarotation. So building off of that ibuprofen idea. So about the polarimeter that measures how light rotates through a molecule as it's changing into a different type of ring or form, ordinary light vibrates in many directions and is called unpolarized light, and a polarizer forces the light to vibrate in only one direction, creating polarized light, which is just like a focused laser beam. The analyzer inside the polarimeter is a second filter that can be rotated to test the direction of the polarized light. And when it's rotated to a position where no light is seen, it is perpendicular to the light's vibration direction. That might be confusing, but if you see the image of the plane of vibration of polarized light, you can see that when the light rotates by a certain angle, you can then use that to determine what is happening to the molecular structure. Some substances are optically active, so what that means is that they are rotating the light based on their structure and shape. So a polarimeter measures how much the light is rotated after passing through a molecule, and the angle tells us information about the substance and also the concentration. But does that make sense to everyone? I'm going a little bit faster here. Okay, awesome. So originally, I was going to have you guys do another problem with rotation, and it was what rotation angle does the polarimeter measure if we have 53 milliliters of D-glucose here, based on the rotate. 53 degrees millimeter rotation of the D-glucose when there's 10 grams dissolved in 100 milliliters. And I provide you the polarimeter formula, and since we don't have time to go over this one in depth, what you're basically going to do here is that you'll take the length of the polarimeter tube and convert it to decimeters, and then you calculate the concentration of the glucose in grams per milliliter. And then you plug in those two values and the specific rotation, which is 53 degrees, directly into the formula. And the sign of the answer should be positive because D-glucose rotates light to the right. I'll have this formula in the slideshow so you can look over it afterward and use this when creating your projects. But essentially, what happens here is the answer is 2.65 degrees because alpha essentially means the degrees. You put in 53, and then you see that the other two parts of the formula, you just plug in the other information, the concentration, and also the centimeters or decimeters length of the polarimeter. So that actually helps you determine the shape and concentration of something, even if you don't necessarily know what it is, which is pretty cool. So now that we went through some basic concepts, let's go over some uses of stereochemistry. So these include material design, so you can control polymer structure and heat resistance in plastics and composites. You can also develop drugs, such as the ibuprofen that I mentioned earlier. You can make sure that medications bind correctly and also the timing is correct. Also, one stereoisomer can heal while the other may be inactive or harmful. We have catalyst engineering, because scientists can create catalysts that speed up reactions and reduce waste. And lastly, chiral sensors and also polarimeter tools can detect specific enantiomers, which helps with environmental monitoring. So for example, if you know that a molecule is really bad, but its reverse is good, you can use a polarimeter in light rotation to determine which one you actually have in your sample. So now we're going to talk about some more applications that might be more relatable to you. So for example, as we stated before, changing a molecule's 3D arrangement can change its behavior even when the formula is same. So in drug research, it is important to pair enantiomers for the correct biological effect. And polymer stereochemistry controls things like strength and melting point. Asymmetric catalyst may only produce one useful stereoisomer. So if you focus on only producing that one and without producing its reverse, that is useless, then it results in less waste. Here's an example of something that you might see in food. If you reverse S-limonene, you get R-limonene, and those are totally different because one of them smells like a lemon and the other one smells like an orange, even though they have the same exact connections. So here's some more specific molecules that you might have not heard of. So fluoxetine has one effective and potent antidepressant, and its reverse is just not useful. DDT is a terrible pesticide that pollutes a lot. You might have heard of that, but actually, when you reverse it, it becomes even more potent and dangerous. Glucose, as we said before, has two different ring forms. D-glucose is the primary energy source and the sugar that we all care about, but L-glucose is largely indigestible. So they have very different roles in metabolism and also in energy flow. So originally, we were going to have you discuss the influence of stereochemistry in therapeutics and note down any harmful or helpful properties of certain stereoisomers and call on some people to share what they found. But if you look at the form that we sent earlier, which is the challenge, you can go ahead and do this after this meeting and help write your research proposal about a molecule using this prompt. So I'll take the challenge link and send it in the chat again. So after this meeting, if you want to use this prompt to do a web search on the influence of isomers and choose one to research about, that would be really great for the competition. So the last thing that we're going to do, and arguably one of the more interesting parts of this meeting, is going to be using an online simulation to build a molecule virtually. Some of you might have done this before, but as said in the past, this meeting was targeted towards beginners who might have not necessarily had an introduction to stereochemistry and related tools. So if all of you guys could go to app.moleview.com and once you've opened the website, just let me know. Don't do anything on it yet. We'll be building a certain molecule first. Okay, everyone make sure to open that site. It can be on any device. I'm pretty sure they have some mobile support. So we'll also have a video in this slideshow that goes more in depth on how to use this, and you can always review it after the meeting if you're confused about this walkthrough. So once you've gone to MolView, the first thing you should see is an empty workspace with a bunch of drawing tools on the left. And essentially what you can do with this tool is that you can build any molecule that you want in the universe, regardless of whether it exists. And you can look at the molecular geometry and some other properties to determine certain things for research or also just for demonstration, which is very cool. All right, so next, if you see the top of the left menu here, there is a single line. So I'll share the tab as well. If you see in the top left menu, there's just one line there. And then on the right panel, there are a bunch of different elements. Make sure that you have C selected. Once you have C selected, just click on like the white space and you just put down a methane molecule. So once you just did that and you put down a methane, you can see that there's a 3D model of it on the right. And on the top menu, you can click between different models of it. So here is the space fill model, here is the licorice model, and here's just the standard ball and stick model that you saw in earlier problems. So once you just put this down, let us know in the chat. Okay, awesome. So obviously you can do this again after the meeting if you think that it's a little rushed. So now let's do the same exact thing, like a small distance away. let's put down another methane molecule. So essentially what you're doing there is that you just click a little distance away. And now there's 2 CH4s. So tell me when you put down 2. Okay, that's awesome. All right, so next you're going to want to click down on one methane molecule and drag until your cursor lands in a blue circle and release. So it should have turned into a line. And that would turn into an ethane molecule. So let me demonstrate it here. If you just click down and drag towards the other one until a blue circle appears and release, you just connected both of them. So let me know when that. Awesome. This has been pretty straightforward so far. So next, if you go to the Elements side panel and select O, you can click on the end of your ethane and drag down so that the lines create an approximately 120-degree angle. And you just made an alcohol. So that step might be a little more confusing. If you just hover over this, there's like a little gray circle, and you click down and drag, you just added an OH group. Whoops, that was on accident. And now you can see that in red, there's the alcohol that you added. So tell us in the chat when you added an alcohol. Okay, that's perfect. So next what we're going to do is that you can click the turning arrow symbol in the second to last top menu on the right. So if you see this menu on the top that we previously used to switch between models, there's a turning arrow symbol. And if you click on it, it's going to spin 360 degrees. And as you notice, you can see that carbon is the backbone and the oxygen and the alcohol group will change the molecule's behavior. So if you guys haven't taken a class that introduced you to some functional groups, the OH group is called a hydroxyl group. So previously, we just had an ethane, which is literally a hydrocarbon. And once we add an OH, it turns into an alcohol, which is water miscible sometimes and has totally different properties. So now you can do this with literally anything else and add chlorine, sulfur, or whatever you want to it. And it doesn't have to exist, but my challenge is for you to mess with the molecules and see if you can make them chiral. As you can see here, I made a very random model and it does not exist probably in real life, but it's mostly symmetrical, but the mirror image is not superimposable. So you can play with the 3D model and see what's reflection is going to look identical on top of itself and what doesn't, and build something of your own there. So I'll give you guys just 1 minute to spam molecules and literally build whatever you want. And if you guys can, to send a screenshot in the chat. Bonus points if you make something that's chiral. And once you guys send your screenshot, we might be 3 to 5 minutes over time since we had to start late to accommodate to some more people joining. And don't worry if you can't access it right now. We'll send these slides and resources and also a recording after the meeting so you can do any one of these activities later at home. So with a molecular model kit, you can also build these things realistically. And now that you know a lot of essentials about stereochemistry and also messed with a virtual tool, even if you have never done a chemistry class before, you are now equipped to do something meaningful with this information. So for the Sandbox challenge, we are only asking for a 1-page paper, a quick drawing, a small fun project, or a 2-minute video. So anything that is researching a molecule out there, regardless of whether it fully exists or is being used as a medicine right now, then you talk about how it is important in its real-world environmental impact and share with 3 friends or do something or do 3 interesting things in the community about your project. So our competition is due March 1st. And if you just spend 1 or 2 hours to make a small proposal, you'll be eligible for a lot of prizes and group mentorship and also publication as we elaborated earlier. So I'm going to send the competition link one last time in the chat. And feel free to save this for later and work on as the deadline is March 1st. So if you haven't already, feel free to follow Bird2Branch and STEM2Connect on Instagram and save the link to submit to the Sandbox challenge. You can also check us out on LinkedIn, and also we have a lot of other resources and information on our sites and social media pages regarding this. This has been a pretty introductory course, but again, it was intended for anyone who is interested and not necessarily someone with prior experience. But those who submit compelling ideas, regardless of experience, will be able to work on an actual research project and something that's really impactful for the community around them and also on an international scale. So we thank anyone who has joined and stayed thus far. I will send the feedback form one more time. Remember that if you want a certification for the lab and also for your competence in stereochemistry, it is required for you to fill out this form and to attach any notes or files that you took throughout the meeting so that we know you actually participated and were engaged. So now I'm going to open up the floor briefly for any questions. And also as a note, the feedback form is due on Wednesday night, as I would say 3 whole days is enough for you to paste in your notes and submit anything. After Wednesday, we will no longer be giving out any certifications for the form submission. So does anyone have any questions about the challenge or any of the concepts or about prizes or anything else that would be occurring after this meeting?
Yeah, so if you submit the feedback form, you get a certification. Was that what you're saying?
Yes, if you submit the feedback form, you'll get the certification for this event. If you submit to the competition, that'll qualify you for other things such as group mentorship, international publication, and other opportunities that are beyond the introductory things that we went over today. So those are 2 different forms. But make sure to fill out the feedback form if you want a certification from today. Does anyone else have any questions? All right, someone asked, since we have to have a minimum of 3 real-world impacts in the Sandbox challenge, if one was more accessible than the rest, can you continue to redo it? So yes, you can do it as long as it's with different people. So what is acceptable is if you present to 3 different classes about your idea for 2 minutes, that would be acceptable. What would not be acceptable is sending the same friend 3 messages to meet up at the park or something. That would not be related. And then someone asked, what's the other form besides certification? That's to the Sandbox challenge, which is a competition that will be about stereochemistry. And you would just fill out one of 4 different project types. It's either a research proposal, a drawing, a design, or a video. And it would just be 1 page or a 2-minute video max and submit it to that form. That's for the formal Sandbox competition. That's a month long and is due in March. And if you fill that out, you'll have a chance to win a lot of prizes. So for example, we have group mentorship, with people who have published research papers and have also worked at top universities. We also have working with you in order to turn your idea into something that's meaningful. So a huge community service project, internationally recognizing it and pushing out one of your movements, and also turning your project into a fully written research paper or something that is actually published and recognized by faculty. And then somebody asked that this is a monthly thing, and if we could continue to reapply for future events. Yes. So the current competition is about stereochemistry, and we will have another theme after the competition is due on the 1st of March, and then we'll have another event going over the basics of that different topic. And not all of them are about chemistry. So for example, another one could be about a physics concept, for example, or it could be about space and technology, or something about flight. It could be literally anything out there in the universe, and your job would be to connecting it to real-world impact and environmental impact. But yes, I would encourage you to submit to this challenge regardless of whether you like the topic, because you can always connect it to something that you enjoy yourself. You have a lot of freedom to choose what the topic is or what the molecule you want to explore is. You have a lot of freedom over the format, and also you never know if you like future competition ideas or not. So if that's all the questions, we thank everyone who has joined and stayed this far. If you don't like chemistry, we hope we at least changed your mind a little bit. We hope that this was fun and not too hard. Yes, in the rules, you are allowed to create your own molecule, but it has to be actually research. You don't randomly spam different things, connect them together, and then say that it works, right? It needs to be scientifically backed if you want to go that route. But make sure to fill out the feedback form to get a certification and include your name and email in it so we know who you are. So with that, we reach the end of today's session. And if you guys don't have any other questions, you guys are now free to go. But I will be answering more questions for a few more minutes if you guys have them, or if you want to hear other people's questions. Thank you so much for your time, and I hope this was a fun presentation.